Hello, everyone, and welcome to the INQA seminar for today, Tuesday, the 22nd of April. It gives me great pleasure to introduce the speaker, who is Sebastian Schulz from Forschungszentrum Jülich in Germany. And Sebastian will be talking to us today about learning-driven annealing. Over to you, Sebastian.
Yeah, thank you very much, Paul, and welcome everybody to this seminar. So yeah, I will talk about learning-driven annealing, which is a new approach to realize iterative quantum optimization. The idea is that we want to enable the quantum devices that we currently have. So for example, a D-wave advantage system that you can see over here, to be finally able to solve also large-scale optimization problems with thousands of qubits. The problem that we usually have is that these machines typically fail to find the ground state for such large optimization problems and only give us approximate solutions because the annealing times that we can choose are way too small for the large problem sizes. With learning-driven annealing, we overcome this limitation, this bottleneck of short annealing times by stitching together multiple short annealing runs into a global annealing evolution. The main benefit of our approach is that we are not relying on any additional Hamiltonians or changes to the annealing schedule, so something that's always limited by the hardware. Instead, we're only focusing on the problem Hamiltonian. So we're changing and tweaking the biases and the couplers of the problem Hamiltonian. And by doing this, we can significantly simplify the time evolution. We can remove quantum phase transitions during the evolution and reach low energy states with every iteration. I will show you how changes to these optimization problem allow us to guide the time evolution through the Hilbert space over multiple iterations. I will also show you how we can use this to remove quantum phase transitions from the time evolution. I will show you how we can use this as a tool in more complex algorithms to realize something like a local search or global search directly on these machines. And last but not least, I will give you some benchmarking results where we run learning-driven annealing on the D-wave machine against other quantum and also classical solvers. And we will see that we can achieve the same energies in a very competitive runtime compared to other classical solvers running on our supercomputer. So we have a lot of things to cover. Let's start with a quick introduction into iterative quantum optimization. You can see here a typical workflow for quantum optimization. Here on the left-hand side, we have our optimization problem. For the purpose of this presentation, we will consider spin-glass instances, not 7 instances to be exact. These problems are defined as follows. We take our Ising Hamiltonian, we set all the biases to 0, and all the couplers, they are chosen uniformly from this distribution over here. You can see an example of such a spin-glass problem here for the D-wave advantage 5.4 system, so 5,580 qubits. Each of these black dots, this is an individual qubit, and all the connections between these dots, these are the couplers that we randomly choose here. You can see that this system is frustrated. It has disorder, so typically it's very hard to solve. On average, these problems have around 2 to the power of 50 different local minima, low energy local minima. And also these local minima, they are separated by high and wide energy barriers. So the typical Hamming distance between 2 local minima is in the order of like 500 to 600 qubits. So they're very hard to solve classically. And what we want to see is how we can solve them using a quantum computer. And of course, we do this. We take our Ising Hamiltonian, we submit this to the D-wave machine, and at the end we get a bunch of samples, so a bunch of states from the quantum annealer. You can see each blue dot, this is a separate state that the D-wave system prepares. You can see on the x-axis, this is the Hamming distance to the best known state that we call here solution state, and on the y-axis we have the energy distance to this solution state. And what we see here is that already when we use the full, so the maximum annealing time that we can choose, so 2 milliseconds, we can see that we get this cloud of states where even the best state that we sample still has roughly a Hamming distance of 1,000 to the best known state, so to the solution. And this is a typical picture that we see for these large problems. These devices can prepare very good states very fast, but they're failing to really reach the ground state or the solution to these optimization problems. So in order to overcome this bottleneck, the idea is that we use some sort of iterative procedure where we run the problem on the device, learn from the samples, and tweak the algorithm somehow in order to reach lower energy states with every iteration. A typical example how to do this is to change the annealing schedule. So what we could do is like make the annealing slower near quantum phase transition so that we increase the probability of staying in the instantaneous ground state. In the most extreme case, we can also do something like QA, where we have full control over the driver and the proper Hamiltonian. But when it comes to implementation, these things, we're very limited by what the hardware actually allows us to do. So on the DWF system, for example, we can tweak the annealing schedule to some extent, but it always has to be monotonic. There's a maximum slope that we can set. There's also fixed initial and end points. So we can only tweak this to some extent, and this will not allow us to actually reach the solution state here. Another approach is something like reverse annealing or cyclic annealing, where we start from a very good initial guess, and the hope is that we can initiate this annealing process from this initial state in order to reach somehow lower energy states. I will later show you some benchmarking results on reverse annealing and cyclic annealing, but it turns out that these strategies are heavily limited by the thermal temperature, so the effective temperature of the chip. So they can improve in energy, but they also hit like a hard limit, and they cannot reach the solution state either. So we see that tweaking the algorithm is not really an option. While it works well in simulations and on paper, due to the hardware limitations, this will not help us to reach the actual ground state. So what we do is something different. We cannot change or tweak the algorithm. So the idea is that we change the optimization problem itself. So we take our optimization problem and we simply remove some of the couplers, some of the biases. This is something that we can always do on any quantum device, on any for any optimization problem. So we're not limited by the hardware in any way. And the idea with learning-driven annealing is that we get all these samples from the quantum annealer, and in a sense, they already are a good guess to which region of the Hilbert space low energy states are located. So which region of the Hilbert space we should focus on and explore more. And the idea is that we take these samples, we analyze them, we can relate them to certain structures in this problem Hamiltonian, so to certain couplers, to certain biases. And by amplifying these biases and removing others, we can simplify the optimization problem. We can remove phase transitions and reach lower energy states with every iteration. You can see a small example here in this animation. So we start with these blue dots here, which are the samples from the quantum annealer. We then modify the optimization problem a little bit, and then we obtain these red samples. And we continue doing this, get the green samples, and finally these purple samples. And as you can see here, already after 3 iterations, we are able to reach, in this case, the best known state with a very high probability. The big question, of course, is what changes do I need to do to this optimization problem in order to obtain a process that looks something like this? And to explain this, I have prepared a small toy problem. This is a 24-qubit spin glass instance. It's similar to the large one that we saw before. The only difference here is that we have these dashed lines here, which denote periodic boundary conditions. So this qubit is connected via this dashed line to this qubit here, for example. We do this to make these problems a little bit more interesting, although they are relatively small. We also add here some small biases. These are roughly an order of magnitude smaller than the couplers, just to lift the degeneracy of the energy landscape. Here on the right-hand side, you can see the instantaneous energy spectrum for this 24-qubit spin glass. You can see some of the instantaneous states here. And what we can see is that we have some closing gaps here. So here's a closing gap, also here and also here. Keep in mind that this is normalized between the smallest and the largest state here. And yeah, you can see here by looking at the color of these lines, how the measurement probability, how the system spreads across these states. You can see that there's some significantly spread here, and we in the end we sample some superposition of like all the states, all the energy values in this optimization problem. So the big question is, what changes do I need to do to this optimization problem in order to lift these small energy gaps here and, in the best case, remove these phase transitions? And to understand this, we have to take a step in between, and that is to look at the energy landscape. So how is the energy landscape? How are these local minima related to certain structures, certain biases and couplers in the optimization problem? So yeah, here you can see the energy landscape for this 24-qubit problem. The z-axis is the energy, and the x and y-axis, these are Hamming distance. You can see this grid on the surface here. So one step is exactly flipping one qubit. You can see these labels here, alpha, beta, and gamma. We use them here to label the 8 local minima of this optimization problem. They're also shown here by these colored diamonds. And a very important insight from our research is that you can identify these local minima and also these states around this local minima, so this energy valley essentially, through certain structures, so couplers and biases within the problem Hamiltonian. We call the structures features. So feature is basically you take any state, let's call it alpha, and all the set of biases and couplers in the problem Hamiltonian that is satisfied, this makes up a feature or the features for this specific state alpha. What do I mean by satisfied? I mean that the contributions of the biases and the couplers reduce the overall energy for this specific state. So if you would go through the calculating the energy for the state alpha, you have the sum over all the biases, over all the couplers, and each term that is negative, you say, okay, this bias, this coupler is now satisfied. And if a term is positive, so for example, h times the respective qubit is positive, then it's increasing the energy, so we say it's not satisfied. To give you an example, we have here this blue local minimum and this purple local minimum, and the set of satisfied couplers and biases looks something like this. The unsatisfied terms here are shown in white, and the satisfied couplers and biases are shown in this gray and this black. I use here 2 different colors for the couplers because they can be satisfied in 2 different orientations. So this allows us to distinguish in which orientation a coupler is satisfied. So we have this collection here of satisfied terms, so couplers and biases, and these are essentially the reason why we actually see, why we actually have this state here as a local minimum. So the energy reduction that they cause is the reason why we see that this is a minimum, why we have here an energy valley around this state. And if you would remove this, so all of these couplers, all of these biases, then at this region of the Hilbert space, the energy landscape would just be flat. So there wouldn't be any local minimum. What we can do now is we can compare these sets of satisfied couplers and biases between these local minima. So for example, if you look at the blue local minimum and the purple local minimum, you can see that they are almost identical, except for this middle 8 qubits. So these 8 qubits and these 8 qubits here. And basically, this blue state has all the opposite couplers and biases satisfied compared to this purple state. And if you now compare this not just between these 2 states, but between all of the 8 local minima, we'll see that these local minima always differ in these groups of 8 qubits. I highlight them here in green and purple and orange. These groups of 8 qubits we call spin domains, and these spin domains you can think of as a group of qubits that is highly correlated. And you can see the energy distribution within these domains here. So on the x-axis, we have Hamming distance, on the y-axis, and energy. So this is just within one of these domains, for example, here the green domain. And you can see that we always have 2 low energy states that are separated by some energy barrier here. And this energy barrier is exactly what we see here in the energy landscape. So for example, if you want to go from the red state to the green state, we have to go from the beta configuration to the beta bar configuration. So we have to cross this energy barrier here. And this is exactly what we see here. So this is exactly this energy barrier here. The important observation now is that these two low energy states within these spin domains are described by the features that these states have in these domains. So for example, for this purple domain, you can see that we have this feature satisfied here, and the opposite one is this feature satisfied here. So this describes here beta bar, and this here describes beta. And with this knowledge, we can look again at the instantaneous energy spectrum. The 8 states that we see here, these correspond to the 8 local minima in the end. So all these states in the end, these are exactly these 8 local minima. And we can see how probability amplitude is transferred across these energy values over the annealing time. You can see that we have here closing gaps. So here's a phase transition, also here and also here. And you can also see here the ground state magnetization with these 3 steps that we have in here. And each step describes, in this case, a second order phase transition, where we go from a delocalized state, so some superposition state, to some localized state. And interestingly, these phase transitions, they directly correspond to this internal structure of the optimization problem. So the first phase transition just deals with the first spin domain, so this green spin domain here. And essentially what happens is, right before this phase transition, the system is in some sort of superposition of these states here. And right after the phase transition, it has to decide. So it localizes either in this alpha state or in this alpha bar state. So it's then just a superposition of this right arm or this left arm over here. And so the small energy gap that we see here between these instantaneous states here is exactly due to the small energy gap that we see between this minimum state and this minimum state over here. And the idea now is that since we can relate these phase transitions directly to certain couplers and biases within the problem Hamiltonian, we can remove these phase transitions just by removing some of these features. So some of these biases, some of these couplers. To give you an example, let's consider this purple transition here, which corresponds to this purple spin domain. And what we'll do is we create something that we call a feature Hamiltonian. Feature Hamiltonian is exactly like the normal problem Hamiltonian, with the only difference being that we remove all these unsatisfied terms, given some reference state alpha. So what we do now is we take this purple domain here. We say we want to prepare this, for example, this beta bar state. So we want to ignore all the features that correspond to beta here. So what we do is we take the state, we remove all the unsatisfied terms, just set them to 0. And for all these satisfied terms that you see here in this domain, we do this transformation shown here. So what this does is it leaves the biases unchanged. But for the couplers, we do this transformation, which basically just adds 2 biases to the 2 qubits I and J. The reason why we do this is to lift the degeneracy of the couplers. So usually they can be satisfied in both orientations, so alpha I and alpha J, and both qubits flipped. By adding these biases, we make it such that this term here only gives us a negative energy contribution, so can be satisfied only if you're really, so if both qubits I and J are in this configuration alpha I and alpha J. And what I will show you now is an interpolation where we go from the problem Hamiltonian to this feature Hamiltonian. Let's start here with the energy landscape. You can see as we increase the strength of our feature Hamiltonian, we significantly simplify our energy landscape such that at the end, we are left with an energy landscape where we have removed many of these local minima and energy values. So you can see all these 4 energy values that used to be here, they're now completely flat. And you can prove that this region here, so this configuration of beta that we don't want to consider, this becomes completely monotonic in Hamming distance. So it always points into the direction of the part of the Hilbert space that we want to focus on. And if you now look at the instantaneous energy spectrum, so what happens to it? Again, we focus on this transition here, which is the transfer from this line here, from this state to this line here, to this state, and from this state to this state over here. So essentially these 2 states here, these 2 lines here are important. And as we increase the strength of our feature Hamiltonian, you can see that we move them up. So we increase here the energy gap between them until eventually there's not really an energy a closing energy gap anymore, because the subspace of the energy landscape within this domain becomes completely monotonic. So there's not really two states that close up. And what you can see is that the measurement probability is now confined in these 4 states over here. So this exactly corresponds to this part of the Hilbert space, and we do not measure any state anymore in this part of the Hilbert space. You can also see this here in the ground state magnetization. The second phase transition is now completely gone. We're only left here with the phase transition in the first domain and in the last domain. So as a small recap, we learned that we can identify these local minima and energy valleys through features within the problem Hamiltonian, so certain sets of satisfied couplers and biases. And we saw that the internal structure, so the spin domains, corresponds directly to these phase transitions that we see in the instantaneous energy spectrum. And by removing these features from, so within these spin domains, we can remove phase transitions and we can steer the quantum evolution, so time evolution, into a specific subset of the Hilbert space. Of course, this alone does not solve any optimization problem. We can view this more as a tool to guide the time evolution. And next, I will show you how we can actually use this to solve an optimization problem. We do this, or the process, we call it learning-driven annealing. The basic idea is that we use this idea of focusing the time evolution to a certain subspace of the Hamiltonian based on the samples that the quantum annealer returns. As an example, let's consider we have measured somehow these 4 states over here. What we do first is we create this feature Hamiltonian HF for each of these states separately. So you can see them over here. So we have these 4 different feature Hamiltonians. And each Hamiltonian alone would describe an energy landscape that is pointing monotonically to this one reference state. And what we do now is we compare these 4 feature Hamiltonians, and we only keep those couplers and biases that are satisfied by all of these states. You can see that this is mostly the case here for the third and for the second domain, while in the first domain, these states do not really agree, and we have many qubits here that are not even connected or don't even have any biases attached. So what this does is it creates an energy landscape that has a specific region in the Hilbert space where it's flat, and outside this region, it becomes monotonic. So we remove all the local minima, all the energy valleys outside this region, and we can focus the annealing only within the small part where all the states are scattered. You can see this here as an example. You can see here that the energy landscape is monotonic. First of all, you can see that we have energy distinction in beta. So here you can see that the beta bar states have a higher energy than the beta states. You can see the same thing here for the gamma states. So these gamma bar states have a higher energy than the gamma states, but within alpha, so being in this state or here, it's more or less constant. So it does not really distinguish within the first domain. So what we do next is we add back the original problem Hamiltonian. The goal is to have in this space where the energy landscape is mostly flat for the feature Hamiltonians, to add back the original problem Hamiltonian, so add back the energy values and so on, so that we can focus the annealing on this subspace of the Hilbert space and explore where then low energy states might be located. And you can see that, so we add it back here. So we add the problem Hamiltonian back to all the couplers and biases where here the states do not agree. So this is mostly the first domain. And you can see that here we get the energy distinction between alpha and alpha bar. And between them, we have here a higher energy, the same up here. And when we now combine these 2 Hamiltonians together, we end up with the final Hamiltonian that we use in learning-driven annealing, which is monotonic and just has this one local minimum that's located here. So just by having these 4 states somehow distributed in the energy value of this local minimum, we can create energy landscape in Hamiltonian that has the ground state, so has this local minimum as the ground state, and has removed all the other energy values from its energy distribution. And by doing this with high probability, we'll now obtain a state that has a lower energy or is even the ground state, just given these four sampled states. So this is exactly what we do. So we take this Hamiltonian, we run it again on the quantum annealer, get a bunch of states out of it. We translate them in energy back to the original problem Hamiltonian. And then as the last step, we have some protocols to select which states we use in the next iteration as a reference. Then this whole process just continues until we find a state that has a low enough energy or is the ground state. This last step here, these protocols for selecting the sampled states is actually very important because it also allows us to implement different kinds of searches. So for the spin glasses, we implemented a local search protocol and a global search protocol. But for other problem kinds, we can also imagine different kinds of protocols. We can use some information like having certain constraints that need to be satisfied. So we can select the state space also on that. So here regarding the local search protocol, the idea is that we start with some initial state, for example, this black dot over here. And the idea is that we want to reach the closest local minimum. So we are in some energy valley and we just want to go down to the local minimum. The way we do this is we take the feature Hamiltonian of this black state, so our initial state, and just sample from this feature Hamiltonian. And you can see that we obtain then these blue states over here. So it's some distribution around this initial state. We then take the best, in this case, I think 8 states. We construct this joint feature Hamiltonian, add back the problem Hamiltonian to some degree, and this gives us then these red samples. We continue in this fashion, we get the green samples, and finally the purple samples. So you can see that we traversed a distance of roughly 80 qubits, so 80 spin flips, and found here a lower energy state with the local minimum of this energy valley. So this is for the local search. We also designed a global search protocol where the idea is that we are currently located at the local minimum and we want to overcome the large energy barriers between the energy valleys and hop into a lower energy valley. And moving up, so being down here and just move up in order to cross this energy barrier is actually very, very hard because, as I said, it's very wide, like 600 qubits, very high in energy. So we use a different trick here. The idea is that we come from the top, from the outside, and we focus the annealing or converge time evolution to a subset of the Hilbert space that's gradually shrinking around this initial energy valley. And if we do this, there's a high probability that we actually fall into another local minimum, which then has a lower energy. So you can see this here. We start here with this local minimum. And initially, we then sample from the unmodified problem Hamiltonian, which gives us these blue samples here. We again take the best 8 states. And then we construct a joint Hamiltonian between them, so the joint feature Hamiltonian. We compare this feature Hamiltonian then also to this initial state. And again, we only keep those biases and couplers that is satisfied both by all of these states, but also by our reference state. So this basically denotes a certain region in the Hilbert space where we want to move to. And by doing this, we then obtain red samples. Again, we continue in this fashion, get the green samples, and finally the purple samples. And you can see here these 3 arms of states that we sample here. And these 3 arms, they denote 3 different energy values. So you can see the original that we started from, but also this one, which has a Hamming distance of roughly 400, and also this one, which has a Hamming distance of around 600 qubits or spin flips to the initial state. And as you can see, we are already after 4 iterations, we are able to cross these high energy barriers and find a new local minimum that has a lower energy. And you can also see here how we changed the problem Hamiltonian over time, over these iterations. Black dots denote qubits where we didn't apply any changes, and the colored ones are ones where we use this feature Hamiltonian. You can see here for the first iteration, so this red samples are obtained by changing these qubits here. So you have these colored spots where we applied the feature Hamiltonian. Then for the second iteration, the green samples we obtained by also fixing these qubits here. Then finally the purple iteration, here we fix these qubits here. And just by the shape of these qubits, you can, in some sense, you can see how the spin domains within this large optimization problem actually look like. Finally, I have some benchmarking results. Here we compare our hybrid solver, which uses these two protocols, local search and global search, on 10 randomly generated NAT7 instances, all using 5,580 qubits. You can see in the first row, these are the results that we obtained for the first problem instance, and all the other instances are shown down here. So the first columns here, this is our hybrid algorithm using learning-driven annealing. You can see that we start with the initial state, which is just obtained from normal forward annealing on the D-wave. And then here we apply the local search, then a global search, local search. So we always use them in this alternating fashion. And after nine iterations, we already find here the lowest energy state that we know for this particular problem instance. And this only took us six minutes. We also compare this here against other quantum strategies. You can see in orange, this is just normal forward annealing using 10,000 samples for each dot here. You can see it just scatters around this middle value here. This is corresponding to this cloud that I showed at the beginning. And we also test reverse annealing and cyclic annealing. You can see that they improve in energy, so they can give us lower energy states, but they quickly saturate as they're limited by the effective temperature of the chip. And you can see also here they only make small changes to the quantum state, so to the bit string. So from iteration to iteration, they maybe change like 10 qubits or 20 qubits. But of course, this is not enough to overcome this big energy barriers of like 500, 600 qubits. So they're essentially just doing a local search here. We also compared against classical solvers. So we have here simulated annealing and also some proprietary solvers like Gurobi, Toshiba, and D-Wave Hybrid. Interestingly, here the simulated annealing performed best. So we were able to reach, at least for two problem instances, the same energies as our hybrid solver here within the 24-hour time limit. One thing to note here, of course, is that the runtime for the classical solver scales inverse proportionally to the classical resource that we give. So in this case, we use one node of our supercomputer, so 4 Intel Xeon Platinum CPUs. But of course, if you would use more classical resources, like 100 nodes maybe, then this would, of course, converge faster. But this already shows that the D-Wave itself is a very efficient device, so it can produce good states in a very short amount of time. And by using these iterative procedures like our learning-driven annealing, we can actually make use of this and obtain good results in a very competitive runtime to other classical solvers. With this, at the end of this presentation, so what we learned is that the hardware limitations like short annealing times, limitations to the annealing schedule, the effective temperature of the chips, they necessitate iterative protocols that in some sense can guide the quantum evolution through this Hilbert space. A possible example to do this is our learning-driven annealing, which is based on the idea of satisfied terms, so special structures within the problem Hamiltonian that we can relate to quantum phase transitions. And the idea is to suppress these terms, to suppress these features in order to prevent quantum phase transitions, to control the exploration of the Hilbert space, so like focus on different parts of the Hilbert space. And as we saw here, we can use this to enable some practical quantum computation, some practical quantum optimization using the devices that already exist today. And with this, I'm at the end. Thank you very much for your attention. And if there are any questions, happy to answer that.
Great, thank you very much, Sebastian. A round of applause on behalf of the audience. And as Sebastian says, we have some time for questions. So if you have a question, either raise your hand or turn your camera on, or just speak up or put something in the chat, or any other method you like, of which there are many.
Hi, can you hear me?
Yeah, hi.
Oh, so hello all, and thank you, Sebastian, for this webinar. My name is Pablo, and I work in the quantum division of Tecnalia, which is a Spanish company. And well, I've signed here to this webinar because I've already seen this paper when you upload it, and I find
Yeah.
this technique really interesting. And I have some questions. I don't know if you could elaborate a little bit on how do you relate each second order phase transition to each domain in the, like it's one of the first graphs that you showed us,
I
in which
think
you have the, yeah, that one.
well, something like this, yes. Yeah, so in general, when it comes to quantum annealing, we have these two kinds of phase transitions that we can have. So we can have a delocalized to localized transition, which means we're in some sort of superposition, and after this transition, the system has localized in like one arm of this local minima or this energy values. This is typically what we see for the spin glasses. So we have lots of these. Yes, in this case, these are second order, so this gap closes polynomially. And the other type of phase transition that we can have is when the system's already localized in one of these energy valleys and then has to tunnel through the energy barrier into another energy valley, so like the ground state valley. It's not something that we typically have for the spin glass problems. We have this for other types of problems, like weighted maximum independent set. You can find these. Yeah, the thing, what makes these spin glasses so hard, even though they're just like second order phase transitions, is that the number of these second order phase transitions scales exponentially in the number of qubits. So even though they only scale polynomially, we have exponentially many of them, which then makes it hard and exponentially hard to solve. Yeah. Does this answer a question? Or
Yeah. So for this to work, do you need to assume that in between spin domains there is like low coupling between them, or is this like general?
this is general. So the structure of the spin domains is something that we often see for the or that we generally see for the spin glasses. Makes it nice to visualize. But you can also have other kinds of domains. For example, I have also here an example of a weighted maximum independent set. So this is another problem where we have two domains, a 6-qubit domain, a 12-qubit domain, which is completely connected. So all qubits here are connected to all qubits here. And we use the coupling here. So we choose this kind of coupling here, which essentially removes one of these local minima, which would be located here. And what we have here is a small energy gap between here, this local minimum, and the first excited state, and a large gap here. And this, as you can see here in the ground state magnetization, gives us a first order phase transition. But you can use the same procedure also here. So if I apply here this feature Hamiltonian, you can see that we increase here this gap, and at some point here, basically we don't have any first order transition anymore, it's just second order, until the end where the energy landscape becomes completely monotonic, and then there's basically no phase transition anymore happening. So it's generally applicable. Just depends on which kind of protocol that to use in this learning-driven annealing approach. So for the spin glasses, global search works very well. If you have other problems like two-set where you know what the constraints are, you can then select the states differently, and can also speed this up then. Yeah.
Okay, that answers my question. Thank you very much, and congratulations.
Yeah, thank you. Other questions?
Other questions, as Sebastian says. I'm the chair, Sebastian. Maybe I can have a question, and maybe you've kind of already explained this, but I guess spin glass instances, the interactions are native to the architecture of the D wave.
Yes. This was the reason why we investigated them, because we wanted to study large optimization problems, because often, I mean, when you cross like 1,000 qubits and more, then these problems actually become hard. And we had to find something that's native to the device so that we can have these large problems. Yeah.
But is there any reason to believe that the underlying interaction graph defined by the deep architecture is particularly well suited or not well suited to this technique? And if you had a random interaction graph, would your technique?
So we have simulations. So we have simulations up to 40 qubit problems with all-to-all connectivity. So spin glasses with all-to-all connectivity. And it also works for these problems. So you can kind of expect that this is a general thing. What makes it nice for the D-Wave, of course, is that, for example, here you can see how the spin domains look like for 5,500 qubit problem. You can see this like blobs of same color. So these are spin domains here. So we obtained them from investigating hundreds of local minima. So in this case, we end up with like roughly 50 of them. And you can see that they're spatially like connected or close. So this is because the D-Wave has just a spatial connectivity. So this makes it easier to solve, of course. You can also use some other classical techniques, maybe solve this in parts or something like this. But yeah, from our simulations, at least, we expect that this is also true for larger problems with high connectivity. Okay.
Any questions for Sebastian? If not, let's thank Sebastian once again for a very interesting and thought-provoking seminar. I think I'm right in saying that next week there is no seminar because it's a public holiday in Japan. So the next, maybe I should check this fact before I say it. So the next seminar, I'm right, will be on May the 6th. And that will be given by Kartik Agarwal, who I think is from the Argonne National Lab in the US. So I look forward to seeing everybody in 2 weeks' time. Thank you, Sebastian, and enjoy the rest of your week, everyone. Bye-bye.
Bye.